Welcome to The Explainer. Today we are going to dive into a classic Python puzzle that, let's be honest, can trip up pretty much everyone at some point. It's all about what happens when you mix something that can change with something that can't. And it really gets to the heart of how Python thinks about data. So this is the big question, right? We know lists are mutable. You can mess with them all you want. And we know tuples are immutable. Once you make them, they're set in stone. So what happens when you put an immutable thing inside a mutable thing? Who wins? Does the list's flexibility take over, or does the tuple's rigidness just break everything? It's a fantastic question, and the answer is super revealing.
And I'm willing to bet that if you've ever tried to just, force an answer in your code, you've been greeted by this exact frustrating message, type error. It pops up, your script dies, and you're just left scratching your head. Well, today, we're going to demystify this thing for good.
Okay, so the key to solving this whole puzzle lies in making one simple but really powerful distinction. We've got to stop thinking of our data as just one thing and start seeing it for what it truly is, two different parts, the container and the contents inside. First, let's just do a super quick refresher so we're all on the same page. When we talk about mutability, what we're really talking about is the container. Can you add stuff to it, remove stuff from it, or swap things out after you've made it? If the answer is yes, well, that container is mutable. It's as simple as that. And that brings us to the two main characters in our story. You've got the list with its square brackets. That's Python's go-to mutable container. And then you have the tuple with its parentheses, the classic immutable one. One is literally designed to be changed, and the other is designed to be permanent. So here are the rules of the game. Can you modify the list itself? Add things, remove them, change the order? Yep, absolutely. The list is a mutable container after all. But what about trying to change an item inside that tuple that's sitting in the list? No way. That is a hard no. The tuple's contents are totally locked. But, and this is the big twist, you can take the entire tuple out and replace it with a whole new one. Why? Because that's a change to the list, not the tuple itself. Now, rules are one thing, but to really make this concept click, let's use a couple of analogies that I think perfectly illustrate this idea of a mutable container holding an immutable item. For our first analogy, I want you to picture a regular old cardboard box, and inside it, there's a sealed envelope. So think of your list as that cardboard box. You can open the box whenever you want, you can put more things in, take things out, or even swap one thing for another. The box is completely mutable. Now, one of the items inside that box is a sealed envelope. That's our tuple. You can take that whole envelope out and replace it with a different one, no problem. But what you can't do is tear open that specific envelope and try to edit the letter inside. The envelope itself is sealed shut. It's immutable. Okay, here's another way to think about it that might be even more intuitive for some of you. Imagine a 3-ring binder, and it's holding a laminated page. Your list is the binder itself. You can open those rings anytime to add new pages, take pages out, or just shuffle them around. The binder is totally mutable. But one of those pages inside is laminated, and that's our tuple. The text on that page is permanent. You can't just take an eraser to it or write over it. But could you open the rings and swap that entire laminated page out for a new one? Of course you can. You're changing the contents of the binder, not the permanent text on the page itself. All right, those analogies give us a really good gut feeling for how this works. Now let's bridge that intuition over to the real world and see how this actually plays out in Python code. So here's our test case. We've got a list called list1. It's got some integers in it, and then boom, right there at index 3, we have our tuple with the numbers 4 and 5 inside. Okay, first, let's look at all the things that totally work. We can change the first element, the number 1, to a 10, no problem. We can append a new number, 8, to the very end of the list. Super easy. And check this out. We can completely replace the old tuple at index 3 with a brand new tuple, 8, 9. All of these operations are success. And why do they all work? Well, it's because in every single one of those cases, we were messing with the list itself. We were changing the binder. We were rearranging the box. We were changing the container. And the container is built to be changed. But now, let's look at the one line of code that brings the whole thing crashing down. Here, we're trying to reach into the list at index 3, which gets us our tuple. And then we try to go one level deeper, into the first item inside that tuple, and change it to 99. And this is where Python puts its foot down and throws that type error.
We aren't changing the list anymore, are we? We're trying to alter the contents of the tuple. We're trying to write on the laminated page. We're trying to break the seal on the envelope. And that is something the very nature of a tuple will just never, ever allow.
So after all that, what's the one golden rule you need to walk away with? The one thing to remember from all this? This is it. A container's ability to change is completely separate from the ability of its contents to change. The list's power to be modified only applies to its own structure. It does not give you some magical power over the fundamental rules of the objects you put inside of it. A mutable box can't make a sealed envelope unsealed.
And that leaves us with a final thought to chew on, because this principle doesn't just apply to lists and tuples. Think about it for a second. What do you think would happen if you had a dictionary, but you used immutable tuples as the keys? Or what about a list that contains frozen sets? The exact same logic applies, and really understanding this core difference between a container and its contents is going to make you a much, much sharper Python programmer. Thanks for watching.